Okay, so I mentioned that the word instabilities driving motion. Let's go through some simple derivations of what an instability is, right? I am quite certain you have seen this in some physics class or some other thermodynamics, dynamics course somewhere, fluid mechanics and so on. So we're going to try to look at these two situations, a little ball sitting here at point A on top of a hill, and B, which is at the bottom of the hill, okay, in a valley. So what are the forces here? If it's sitting right here and you don't perturb it, it's stable, but is it a solid stable situation, or is it conditionally stable? If you push it a little bit, what happens? Will it come back to its original position, or will it go off into a new position? That's kind of the intuitive sense of instability or stability, right? As you can imagine, if you push this a little in either direction, it's going to go off to the bottom of the hill, whereas this one, if you push it a little, it's going to swing back. Why does that happen? Obviously, there is a force balance involved. So let's define the perturbations, and for a small slope, minus dg times dh dx is the force that's going to pull it down the slope. So if you push it just a little, and this is the slope dh dx, it's the slope of this hill, and g is the gravitational pull, so the net force is going to depend on the slope of the hill, right? So gravitational acceleration along the slope is given by minus g dh dx, which I'm sure you can understand with the knowledge you already have. The other basic piece of information we will need, the concept we will need, is called Taylor expansion. So a quantity Rx here can be expressed as a constant, it's a function of x, plus c1 x minus xa, c2 x minus xa squared, and so on. What does that mean? You can expand Rx into a series where the slope of Rx, dr dx d squared r dx squared, are going to determine the terms in the series. So if you move it away by a little bit xa, then the value of Rx is going to be determined by the slopes, and slope of the slope, second derivative of the slope, and so on and so forth. Why? Because we are going to look at this situation. There is a slope, and then there is a slope of the slope. So if you go from here to here, you are going from positive slope because you go in x, h increases, to a negative slope because you go in x, h is going to decrease, right? That's where we are headed with this. So r at a small perturbation from its position A at the top of the hill, delta x, r at x A, top of the hill, plus delta x, a small perturbation, is going to be determined by r at x A plus delta x times dr dxa plus delta x squared over 2 factorial times d squared r dx squared, and so on. Okay, so dh dx itself also can be expressed this way. So the change in the slope, if you move slightly away from xa at the top, remember it's sitting at the top because the slope is 0. The slope is positive, 0, and then changing to negative, right? So if you get away a little bit delta x from xa, the top of the hill, the slope is going to change to dh dx at xa plus d squared h dx squared at a, second derivative of the slope of h at the top, times delta x. So dh dx is 0 because it's flat at the top. So changing the slope slightly away from a is going to be d squared h dx squared at a times delta x. Very simple math, no need to panic. Just make sure you understand it. So how do we write the equation of motion? It's basically the acceleration of the change of the position. So the time derivative of delta x is going to give you velocity, and time derivative of that velocity is going to give you acceleration, because we are going to write F equals ma. M is unit, let's say here, unit mass. So d squared dt squared of delta x, a small perturbation, the acceleration is going to be d squared delta x dt squared, which is going to be equal to the gravitational pull. Those are the only two forces acting here. So dh dx is expressed as d squared h dx squared delta x with this Taylor series expansion. It's that simple. We just derived the equation of motion for this ball that's sitting at a stable position at the top of the hill. Okay, so you can then solve this equation, fairly simple equation for its motion. So delta x with time is going to be c1 e to the sigma plus t plus c2 e to the sigma minus t. It's a simple solution for this differential equation. You can figure it out by using Google or some simple math book, where sigma plus minus are the gravitational force that is acting on the ball when you perturb it. Okay, so d squared h dx squared is going from one side to the other side, so you have to just take that into account. That's why you end up with either an imaginary or a real number from this. If d squared h dx squared is negative, then this is going to be positive, so sigma will be positive. If d squared h dx squared is negative, is positive, then square root of a negative number gives you a I, imaginary number. So d squared h dx squared is less than 0, and d squared h dx squared is greater than 0 is going to determine your stability. So we will keep looking for stability conditions as we go along in this chapter. So here it's unstable, because if you push it, it's going to keep going till it hits this bottom, whereas here, if you push it up, it's going to come back. Okay, so that's going to be determined by the second derivative of the slope of h, a second derivative of h in the x direction. Okay, so polenta and oatmeal do not convect. They will burn if you just keep heating them, because they are highly viscous, so you have to keep stirring them, right? That's kind of related to why convection doesn't happen in highly stable fluids. Okay, so I hope you can figure out what is the sign of d squared h dx squared here, and see that here you get a wave solution. So this ball at the bottom of the hill, I think I turned off the okay, the bottom of the hill produce a wave solution. At the top of the